Hello students, now we want to study about periodicity. Before we study about periodicity, do you know what the similarities between periodic table and students' row? Yep, they all have pattern. For example, the higher student will be put in the last line. So does periodic table. The way elements are arranged reveals many beautiful patterns that tell us about how nature operates.
In the middle of 1800s, lots of chemists were trying to come up with a way to depict all of the elements in table form, and many different formats were proposed. But it was the one by Dmitri Mendeleev that stuck, because how well it correlates data as well as its predictive powers. He arranged the elements into rows called periods and the columns called groups. Elements that have similar behavior were put in groups together, which helped to correlate existing data, and it also predicted the existence of elements that had never been seen before. With the gaps in the table, Mendeleev said there must be elements that go in this spot, and he predicted some of their properties. Eventually, these elements were discovered with the properties precisely as expected. And now, we have all the metals, metalloids, and non-metals. It wasn't known at the time, but the reason elements in the same group behave similarly because they have the same number of valence electrons. For example, look at group 1. These elements all have one valence electron, or one electron in their outermost shell. As you go down the table and it increases, you gain a shell each time. But whichever is the outermost shell, there is only one electron on it. Every element in group 2 has 2 electrons in its outermost shell, and so forth.
There are some periodic trends that we can recognize when we look at the periodic table. The first one is atomic radius, or the size of atom.
As we proceed downward on the table, atomic size increases because we add shells. As we go to the right, atomic radius decreases because we are moving within a shell, and each element to the right has one more protons in the nucleus than the last. So, there is a stronger electromagnetic attraction felt by the electrons and the radius shrink. That means atomic radius increase going this way on the periodic table. So, next is ionic radius. Ionic radius is a little different. Electrons repel each other, so adding an electron makes an atom bigger. Taking one away, making it smaller. Ions with the same electron configuration will have their radii decreased as the atomic number increases.
And the second is ionization energy. This energy required to remove an electron from the atom. It will always be an electron in the outermost shell. The electromagnetic force that attracts the electron to the protons drop off very quickly with distance. So, the farther away the electron is from the nucleus, the easier it is to pull it away.
This means the ionization energy trends is precisely the opposite of the atomic radius trends. Francium, A very large atom with only one valence electrons will be easy to ionize because the electron is so far away from the nucleus. An atom like to have their outermost shell completely full. Losing the electrons means the shell is gone and the one below is completely full. So, element in group 1 will easily lose one electron. Looking at the opposite corner of helium, there is only one shell, so the electrons are very close to the nucleus and the shell is full, so it's very stable. For this reason, it requires much more energy to ionize helium. So, the ionization energy increases going this way. Elements can have successive ionization energies for removing more than one electrons. A second ionization energy will always be greater than the first and continue to increase from there. Since the more electron you remove, the less stable the atom becomes. An element will have huge jump in ionization energy after you take the last one in a shell because then you jump to the noble gas electron configuration from the previous shell which is full. So it really won't want to give up any more electrons. There are just a couple exceptions to the ionization energy trend, but we can rationalize them. Look for example at the second row. From lithium to neon, the ionization energy should increase each time we add proton to the nucleus, and the radius contracts a little bit. But something like oxygen, which dip downwards from nitrogen's ionization energy does so, because of orbital symmetry. Here is nitrogen orbital diagrams as well as oxygen's. Notice that nitrogen's 2p orbital are precisely half full. This given nitrogen a special stability, just like elements that have a full. If nitrogen loses an electron, it loses that special ability. But if oxygen loses an electron, it will gain that special stability. That's why oxygen ionization energy is a little bit lower than nitrogen's, even though oxygen has one additional proton. All deviation from the ionization energy trend can be explained by discrepancies in orbital symmetry like this one.
Now, we look at the electron affinity. This is exactly the opposite of ionization energy, since ionization energy is how much energy you need to remove an electron, and electron affinity tells us how much an atom wants to gain an electron.
Disregarding the noble gases as their shells are full, electron affinity increases this way. Fluorine has the highest electron affinity because if it gains on electrons, it will have full shell or noble gas electron configuration. Looking at the opposite corner, these elements don't want to gain electrons. They would rather lose them. Exception to this trend happen for exactly the same reason as the exception to the ionization energy trend.
Lastly, we want to look at the electron negativity.
It will increase this way because a smaller atom like fluorine with more protons for its energy level or higher effective nuclear charge will hold electrons best. Again, we will disregard the noble gases for this trend. So, the trend to remember are atomic radius, which goes this way, as well as ionization energy, electron affinity, and electronegativity, which all go this way.
Okay, class, that's all about our lesson today. Please study at home about chemical bond. Thank you for your attention and see you next time.